Hey calculus kiddos, welcome back to another lesson in the wonderful world of math, focusing on discontinuity today. We're also going to be talking about the idea of what it means to be continuous, because we can't understand what discontinuity is without understanding what continuity is, okay? So our goal is to be able to determine the types of discontinuity of a function. And I'm going to give you fair warning, this lesson tends to be a pretty long one. So with that said, let's go ahead and get started. The first thing I want to bring up is the idea of a continuous function. A function is continuous if it is continuous at every point of its domain. Now, that you look at that and you go, well, that's obvious, but there's some weird examples to this that make it a little bit difficult to comprehend. And so here's the idea. I'm going to give you this one. F of x equals x squared. Okay, well that's easy. That's a parabola. It opens up. Vertex is 0, 0. That is a continuous function. There are no places where it's discontinuous or where it disconnects in any way. Okay? But if I look at the example that I have on the lesson here, when I say f of x equals 1 over x, well, what is the domain of this function? It's probably easier to graph it to understand the domain, but let me go ahead and write this out. The domain is basically all real numbers except for when x equals 0. So from negative infinity, less than x, less than 0, and 0 less than x less than infinity. That's the domain, okay? Now, if we look at the graph of this guy looks like this. Hopefully you agree with that. Where we have a horizontal asymptote and a vertical asymptote. Now, the question is this a continuous function? The immediate answer is, no, it's not a continuous function. But in fact, it is a continuous function. You go, well, how can that be? Because this part of the graph does not connect with that part of the graph. And you are correct. But if you look at what the definition is for a continuous function, is that it is continuous for all points of its domain. Since this function has a domain that does not include 0, then we don't look for any discontinuities at 0, you see. So is the function continuous throughout this entire region from negative infinity all the way up to approaching 0? Yes, it is. Is it continuous for every point after 0? Yes, it is. Is it continuous at 0? No, it's not. Is it a continuous function? Yes, because 0 is not part of its domain, okay? This, we would conclude with this. We would say f of x is not continuous when x equals 0. That's true. It's not continuous. I had to pick up my pencil and set it back down in order to continue in my function. So it's not continuous when x equals 0. But f of x is a continuous function since x equals 0 is not part of its domain. Okay, so I'm just going to leave it there. Generally speaking, the question that we ask is not whether the function is continuous. We ask whether it's continuous at a point. So is the function continuous? I won't normally ask that, but the answer is yes. Is the function continuous at x equals 0? No. And that's the kind of question I'll ask. Where is the function discontinuous? Or what types of discontinuity are there? Or is it continuous at this specific point? Not whether it's a continuous function or not, okay? So the domain of this, again, is from negative infinity to 0 and 0 to infinity. Or you could say all real numbers except x equals 0. Since the domain does not contain 0, then that 0, x equals 0 is irrelevant, which means f of x is continuous, is a continuous function because it's continuous for every other point, which is all part of the domain. And again, however, f of x is not continuous at x equals 0. Okay, there is a discontinuity at x equals 0. Okay, again, our main focus is actually going to be on this this second part here, not the top part. Okay, let's go ahead and take a look at an example of this kind of thing. Here we've got a piecewise function where g of x equals x squared minus 1 for x is less than 2, and 2x for x is greater than or equal to 2. So there's our g of x function. And the question is this a continuous function? Well, in this case, we would say, what's the domain? Well, this is a parabola, so there's no domain restrictions here. This is a line. There's no domain restrictions here. And so the only place of concern is going to be our break in our piecewise. Okay? So if you think of a graph, if you were to graph this, x squared minus 1 is a parabola that opens up with a shift down of 1. But we are only concerned with the values that are x less than 2. So maybe here, we'll call this 2 here. Okay? And that's going to be an open circle. And then 2x, which is here, and going up. So if I plug in 2, I get 4. So this is going to be, looks like this as our graph. 2 squared is 4 minus 1 is 3. So this height is 3. And then 2 times 2 is 4. So this height is 4. So that's the graph of it. The question is this a continuous function? Well, again, the parabola has no points of discontinuity in the sense that it's a parabola. Same thing with the line. So our only question is whether it's continuous at x equals 2. And it's not continuous at x equals 2. So then we ask ourselves, is it a continuous function? So we have to say, is 2 part of the domain? Well, yes it is, because it says x is greater than or equal to 2. So we would say the domain in this case is negative infinity all the way to infinity. Is there any point within the domain that is discontinuous? Yes, there is, at x equals 2. Since g of x has a point of discontinuity when x equals 2 and x equals 2 is part of the domain, okay, g is not a continuous function. Okay? All right. So, but the main question here is it continuous at all points? And no, it's continuous. It's not continuous at 2. Okay? So the domain is all real numbers. Therefore, for its function to be continuous, it must be continuous at every x value because the domain is every x value. It's not continuous at 2, and therefore it's not a continuous function. Now, I did this more analytically on the lesson here. I took the limits. So I said, what's the limit as x approaches 2 from the left versus what is the limit as x approaches 2 from the right? And since I'm going from the left, I'm going to use the x squared minus 1. Since here I'm going from the right, I'm going to use the 2x. And so I can just substitute here. We end up with 2 squared minus 1, which is 3. Here we end up with 2 times 2, which is 4. And since these don't match, that means it's not continuous at 2, and therefore not a continuous function because 2 is part of the domain. And that's kind of where we'll leave that idea. Okay? All right, let's go ahead and go on to what's kind of more important. Continuity at a point. What does it mean for a function to be continuous at a point? Well, I'm going to go ahead and go through the lesson, and then we'll slow it down a little bit. Okay? If a limit as x approaches c of f of x equals f of c, then f of x is continuous at x equals c. Here's the bottom line. If I am looking at a specific point, so let's say I have a graph that that's going along here, and then it stops there. And then there's an open circle. Okay? And what are we approaching here? What's the limit approaching? It's approaching whatever that y value is. Let's say that we continue on. Okay? And so what's the limit approaching from the other side? Well, it's approaching the same value. Okay? So we would say that the limit exists. Remember we talked about that in prior lessons. Is this continuous at that point? We would say no, because it does not equal the function's value. And I guess I'll go through it like this. Okay? Well, let me keep going with the lesson here, and you'll see it. Okay? So I've got a curve, and I've got a c value, which is x, and an L value, which is y. I would say the limit as x approaches c from the left, what is the limit as x approaches c from the left? It's the same as the limit as x approaches c from the right. Okay? Therefore, the limit as x approaches c exists because the two limits, the left-hand limit and the right-hand limit, are the same. And then we can also say, in this case, the limit is L. And we can also say that f of c is L, because at this point, if I move my cursor over to x equals c, I have a height of L. The function exists there. Since the limit is the same as the function's value, the limit as x approaches c is the same as f of c, see, they're both equal to L, that means the function is continuous at x equals c. But you can't have a limit being equal to a function's value unless the limit first exists. How do we know the limit exists? Because the left-hand limit matches the right-hand limit. Okay? So here's what I'm going to say here. Therefore, since they're the same, f of x is continuous at c. Now, here's how I guess I go about it nowadays. I would say this. If the limit as x approaches c from the left of f of x equals the limit as x approaches c from the right of f of x, and that equals f of c, then we would say f is continuous when x equals c. There are three things you need to check for. Three things you need to check for when you're looking for continuous at a point. What the left-hand limit is, what the right-hand limit is, and what the function's value is. So the work would look something like this. I mean, you're going to do more analytic work. This is just notation. Limit as x approaches c from the left of f of x equals L, according to that picture, right? According to the lesson. The limit as x approaches c from the right of f of x equals L. Okay? And then f of c equals L. Left-hand limit, right-hand limit, function's value, all equal the same thing. Therefore, it's continuous at x equals c. Okay? So that's kind of the work here, and then this would be kind of the justification in a sense. Okay? So here's a non-example, and let's look at it in comparison to what we have here. We see that the limit from the left, the limit as x approaches c from the left, is L. The limit as x approaches c from the right is L, and f of c is m. Okay? Not all three of those match. So therefore, this function is not continuous when x equals c. The limit as x approaches c from the left does, in fact, equal the limit as x approaches c from the right. Therefore, the limit as x approaches c exists, and it is L, by the way. Okay? And then we can say that f of c is m. Since those are not the same, then we would say that the function is not continuous when x equals c. Okay. Now, here's how I would write that here. I would say the limit as x approaches c from the left is L, limit from the right is L, f of c is m. Therefore, the limit from the left equals limit from the right does not equal f of c. Therefore, f is not continuous when x equals c. And by the way, all of this would go after that. Okay, so you're going to show the work and then you're going to justify. Okay, that's what it means to be continuous at a point. Now, what about endpoints? And this gets kind of weird, right? Endpoints, if I were to look at a graph, remember when we were talking about limits existing, if I look at, let's say, this graph, and it goes from here to there, and let's say that this is 9, and this is 1, okay? And let's say that this is 4 for the heck of it. The first question I have is, what is the limit? What is the limit as x approaches 1 from the left of f of x? What is the limit as x approaches 1 from the right of f of x? And then what is f of 1? Okay, those are my 3 questions here for this point. Well, the limit from the left does not exist because there's nothing on the left-hand side of the function, of that endpoint. The limit from the right is, well, that's 4. Let's call this 5 just for the heck of it. The limit from the right is 5, and f of 1 is 5. Sorry, yeah, f of 1 is 5. So the first thing I want to state, let me get rid of the f of 1. That's really not important right this second. Since the left-hand limit and the right-hand limit do not match, we would say the limit as x approaches 1 overall does not exist. Okay? Now, go back to f of 1. f of 1 is 5. In the previous definition that I just told you, in order to be continuous at a point, the limit has to exist, and it has to be equal. Well, let me rephrase that. The limit has to be equal to the function's value. Well, the limit doesn't exist. So how could it be equal to the function's value? This is an exception. Okay? Endpoints are exceptions to the definition I just gave you, essentially. Okay? The limit must match the function's value for any point in the interior of the domain. So since the domain here is from 1 to 9, okay, any point in between 1 and 9, to check for continuity, the left-hand limit has to match the right-hand limit, has to match the function's value. But if we're looking at the endpoint, we would say that all we care about is the one-sided limit that exists and the function's value. If those match, then we would say the function is continuous at that point. And so you only have to be concerned with one of the limits, either the left or the right, depending on which one exists, okay? Depending on which endpoint you're talking about, okay? So here's the idea. Well, let me take a step back. I think I kind of explained that pretty well, but let me throw in another point here just for the heck of it. Let's call this 4 and let's call this 7. We would say the limit as x approaches 4 from the left of f of x equals 7. The limit as x approaches 4 from the right of f of x equals 7. And so if you want, you could say, therefore, the limit as x approaches 4 equals 7. And f of 4 is 7. Those are both the same. My lights went out, so let me move around for my lights to go back on. If they'll go back on. There we go. Okay, since the limit as x approaches 4 is the same as f of 4, we would say f is continuous when x equals 4. Okay, that's for an interior point. This is an example of an interior point. Okay, for an endpoint, let's take a look at the endpoint and how we would write that. We would say the limit as x approaches 1 from the right equals 5. And because it's an endpoint, I don't care about the other side. I don't care about the left-hand limit. So we would just say f of 1 equals 5. Therefore, f is continuous when x equals 1. Okay? So if I did as x approaches 9, I would say limit as x approaches 9 from the left is equal to 4. F of 9 is 4. Therefore, f is continuous when x equals 1. Well, let me look at one more case. I'm going to change the graph a little bit. I'm going to put open circle here. That changes my domain a little bit. Now what can we say? We could say the limit as x approaches 9 from the left of f of x. What's the limit? The limit is 4. what is f of 9? Well, f of 9 does not exist because there's an open circle there. Therefore, f is not continuous when x equals 9. Okay, so that's kind of a pretty clear, I think, I hope. Let's go and take a look at a practice problem here. This one's kind of interesting. You might have seen this function before, but you might not have. You have a piecewise function that says f of x equals the absolute value of x over x. Well, I didn't really make that a piecewise function very well, did I? So x is less than 0 there, and 2x minus 1 for x is greater than or equal to 0, and that's f of x. Okay, we are looking for whether the function is continuous over the interval -2 to 0. So within this interval, -2 to 2, within that interval, is this function continuous at every single point? Well, first we want to identify any potential problems. Where is there a potential problem? What are you not allowed to do in math? You're not allowed to divide by 0, and you're not allowed to take the square root of a negative number when you're talking about real numbers here. And in calculus, we predominantly, especially calculus 1, we focus on real number solutions here. So where is there a problem? Well, there's a potential problem when x equals 0, because we'd be dividing by 0 here. And then we have a potential problem at the piecewise, right, when the pieces break off. Okay, so let's go ahead and graph this so we can understand it graphically. What does the absolute value of x over x look like? I don't know. You probably don't know, do you? Well, it's pretty logical, I think, but let's go ahead and do a table just to get an idea. If I'm looking at, let's do a left hand. Well, let's just do a table. Let's do a table. And we want to pick values that are to the left of 0. So I'll plug in like -5, -3, -1. Maybe I'll plug in -0.1, -0.01, because we'll look at the limit too at the same time. If I plug in -5, I get absolute value of -5 is 5 over -5. Well, it's -1. The absolute value of -3, which is 3, over -3 is -1. The absolute value of -1 is 1 over -1 is -1. Interesting. It'll be the same thing all the way through there, right? Because the bottom line is the numeric value of x divided by the numeric value of x is 1. This absolute value is making the top always positive, right? And because I'm plugging in all negative values here, the top is always positive and the bottom is always negative, so I always get a negative out, and then x divided by x is 1. So here we have a graph that looks something like this at -1, and it kind of goes like that. Okay, so that's the graph of the top part, and it's an open circle there because it's not included. And then the graph of this guy, it's, well, 2x minus 1 means you're going to go down 1, and then it's included there, and then we're going to go up 2, and then over 1. So it's going to be something along that line. So that's the graph. And we can look at the graph pretty easily. Is there any point of discontinuity? And the answer is no. Okay? Now, the only place that we're concerned with, if we didn't have the graph in front of us, is x equals 0, because we're dividing by 0 here, and because it's a piecewise break. So I'm going to take the limit as x approaches 0 from the left. I'm going to take the limit as x approaches 0 from the right, and I'm going to go ahead and figure those things out. And then I'm going to figure out f of 0, because of course that's how you check continuity. Check the left hand limit, right hand limit, function's value. Well, the right hand limit is dealing with this. We already talked about this. If I'm plugging in a number that's to the left of 0, I'm plugging in a negative number. If I plug in a negative number here, I get a positive on top and a negative on the bottom, so I know I'm going to get a negative. And then x over x is 1. So the left-hand limit's -1. The right-hand limit, if I plug in 0, I can just plug in 0 because it's continuous. That's just a line. So I end up with -1. 2 times 0 is 0, times -1 is -1. And then f of 0, I'm going to use this bottom part because that's the equal sign. And that will be the same thing as that. Since these all match, we would say f is continuous when x equals 0. Okay? Now, was there any other places within the domain that we had a problem? No. So we can therefore say in the domain -2 to 2 that this function is a continuous function over that interval. So just checking, we got our left-hand limit, we got f of 0, we got our right-hand limit, those all match. Therefore, f is continuous when x equals 0, and therefore it's continuous over the entire interval. Okay? Now, let's jump into different types of discontinuities. Well, I'll write them formally on the notes in a second, but let's kind of explore what is a discontinuity. A discontinuity is anywhere where you have to pick up your pencil and set it back down to graph the line. That's, I guess, the layman's way of understanding it. So what scenarios would I have where I have to pick up my pencil and set it back down? Well, if I have a function that's doing this, and then I have to pick it up, and I have to put it somewhere else, right? That is one type of discontinuity. Okay. There's another type of discontinuity where I'm taking my function, and then I have to pick it up, and then I set it back down right after where I picked it up. That's another type of discontinuity. It might be hard to see that in the camera. But we picked up our pencil and we set it back down just to the right of it, right? And the last type of discontinuity, well, at least that we're going to focus on, is when I have a vertical asymptote. So I got my function and it's kind of going up like this, right? And it's going up there like forever, and I got a vertical asymptote here. Well, I have to pick up my pencil and set it back down on the other side of that asymptote in order to continue my graph. And so these are the three main types of discontinuities that we have, that we deal with in calculus. And so let's go ahead and define those a little bit more in depth. A removable discontinuity is a discontinuity, well, this is an example of a removable discontinuity. We'll go through this example in a second. This graph is an example of a removable discontinuity because the idea is if you can remove the problem, if you can fill in the problem, will it then fix the discontinuity? Well, if we look here, if I try to fill these spots in, it's still a discontinuity because I still have to pick up my pencil and set it back down somewhere else. But if I fill this spot in, it's now continuous at that point. So this is a removable discontinuity. We can get rid of it by just fixing something. And a good example of this is something along this line where we have negative x squared plus 5x minus 6 over x minus 2. Well, where's our potential problem? Remember, we're looking for potential problems when we divide by 0, when we take the square root of a negative number, and then maybe at a piecewise break, right? The intervals of the piecewise. Where am I dividing by 0 here? I'm dividing by 0 at x equals 2. Well, let's see what kind of problem that is. If I plug in 2, I'm going to end up with 0 over 0. That's indeterminate. So I'm going to go ahead and factor this. Okay. There's a problem at x equals 2. I'm going to go ahead and factor this. Now, I'm not going to spend a long time on factoring this, but this is my example of factors. I could have factored out a negative beforehand, but the bottom line is, notice that there's an x minus 2 factor on the top and an x minus 2 factor on the bottom. Those reduce. And what are we left with? Well, we're left with a line. So we have this line that has a y-intercept of 3, and it's got a negative slope. And we have a hole or a removable discontinuity when x equals 2. Why is it removable? Because we removed it from the function. We removed it right here because we are capable of factoring. And so there's the huge clue. If you can factor and then one of the factors from the numerator cancel out with one of the factors from the denominator, that point is a removable discontinuity. So that's kind of cool. A removable discontinuity occurs when a function can be reduced by a factor such that it removes the problem. Now, I've emphasized this in the past. Is this function the same as the negative x plus 3 function? No, it's not. But they are the same everywhere except x equals 2. Because this one had a hole. This whole thing, before I reduced it, had a hole there. Well, when I reduced it, it no longer has a hole. So they're two different functions, but they act the same way everywhere else. It's a removable discontinuity. So if you can factor away the problem, then it's removable. The next type of discontinuity is called a jump discontinuity. So basically you are going from one height and you're jumping up or jumping down to a lower height. And I'm going to tell you a quick story just because I think it's funny, but it scared me too. We were on vacation, and my son got these little laser tag things, and you know the little laser tag guns with the receivers, and you try and shoot the chest plates of the gun, lights up, and you go out and everything. Well, all three of my kids were chasing me. They were trying to get me, so I was running as fast as I can, and there was this ledge that was probably about this tall, and I was running, and I jumped off that ledge, not even thinking. I was running full blast, jumped off the ledge, landed, my feet hit the ground, my legs gave way underneath me, I fell and I rolled. So I rolled right to kind of protect myself, but man, I hurt something in my chest, and it was like that for a couple weeks. I went to the doctor, they said, oh, you're fine, but man, was it hard to breathe. I had a bruised rib, and it was interesting. But anyways, that's an example of a jump discontinuity, because here I am running along the ground, and then I jumped off and I landed on another part of the ground. And so we can see that there's a jump here from here to here. I had to pick up my pencil and set it down somewhere else. Therefore, it's a jump discontinuity. This one, I picked up my pencil and I basically put it back in the same exact place. That's a removable discontinuity. Okay? So a jump discontinuity, here's an example of this. And generally speaking, for jump discontinuities, they are generally piecewise defined. When you see a piecewise function, that's where you might see a jump discontinuity, because this might be a polynomial and this might be a parabola, or you might have a linear function over here and a radical function over here, but they could be in different places. They could be shifted. That's where you get jump discontinuities in general. But we just saw an example of a jump discontinuity a second ago, but we only graphed one side of it. If I look at the graph of f of x equals absolute value of x over x, where's our problem? Well, our potential problem is when x equals 0, because we'd be dividing by 0. So let's go ahead and take my left-hand limit, okay, and see what happens as x approaches 0 from the left. And then we'll figure out our right-hand limit as x approaches 0 from the right, and then we'll compare them, okay? So the left-hand limit we figured out earlier was -1, right? We're plugging in values, well, yeah, we figured that out earlier. We're plugging in values that are negative, and then essentially x divided by x is 1. The top's positive, the bottom's negative, because we're plugging in negative numbers, so we get a negative. Here, if I'm plugging in a positive number, the top's going to be positive, and the bottom's also going to be positive, so we end up with +1. So this graph actually looks like this, a jump discontinuity, right? So that's the idea, or that's one example of a jump discontinuity. We have a problem at x equals 0. The function can't be reduced because that absolute value is in the way. So we check our left-hand limits, we check our right-hand limits, and we see that the left-hand limit and the right-hand limit are not the same, and therefore it's a jump discontinuity. And I'm going to go ahead and, well, I guess I'll define them. I'll show you a little way of checking this in another slide. A jump discontinuity is when specifically the left-hand limit and the right-hand limit both exist, but they do not equal each other. In this case, the limits exist, but they're not the same. Okay, so that's a jump discontinuity. The next type of discontinuity is called an infinite discontinuity. An infinite discontinuity. Well, that's actually our vertical asymptotes. The example that I give you here is 1 over x squared. You should be pretty familiar with what this graph looks like, but we know that we have a potential problem when x equals 0 because we can't divide by 0. So we're going to go ahead and take our left-hand limit, and we're going to go ahead and take our right-hand limit. And you'll notice, just as a quick reminder, I know I got the answers there. If I've got the limit as x approaches 0 from the left of 1 over x squared, remember the rule. The first thing to do is substitute. Well, I end up with 1 over 0 squared, which is 1 over 0. Remember, when you're dividing by 0, you get infinity. Okay, you get infinity. Now the question is, what kind of infinity? Do I get positive infinity or do I get negative infinity? Well, we have to examine the kind of number we're plugging in and determining the signs of the 0, essentially. So we know the answer is infinity, and we know the bottom is 0. But what kind of numbers are we plugging in? Well, we're plugging in negative numbers. So when I plug in a negative number and I square it, I'm going to get a positive number. So essentially this is going to be this is a negative, but when I square it, it becomes a positive, and so this becomes positive infinity. Okay? If I check my other one, limit as x approaches 0 from the right, this one's pretty easy because we're plugging in positive numbers. So 1 over 0 from the right equals, and then I square that, that becomes 0 but from the right, and then that ends up being positive infinity again. Okay? So we look at this kind of graph where it goes up on both sides, right? The vertical asymptote, normally we see a vertical asymptote. I can't say normally, but a lot of times we see it like this, right? The reason this one is going up on both sides, if you would, is because of the square, right? It's making the bottom a positive no matter what. Whereas if I were to look at 1 over x, or maybe 1 over x cubed, let's say, limit as x approaches 0 from the left, well, when I plug in 0, I get 1 over 0, right? And then, which means I get some sort of infinity. But because I'm plugging in negative values, well, I'll go ahead and do that. That's going to be 0 from the left cubed. Well, that's a negative value. So when I cube it, I get a negative value out, essentially, which ends up being negative infinity. Okay? And then if I check the limit as x approaches 0 from the right of 1 over x cubed, I end up with 1 over a positive 0, and then that becomes a positive 0, which is positive infinity. When I say positive and negative 0, that's just my vernacular. Okay? There's not really such a thing as positive and negative 0, but it's easier to think of it that way than to say from the left, from the right, and all that stuff. The bottom line is this: an infinite discontinuity occurs when the left-hand limit or the right-hand limit approaches either positive or negative infinity, or vertical asymptotes. Anytime you see a vertical asymptote, you have an infinite discontinuity. Infinite discontinuity, vertical asymptote, they're the same thing. They're synonymous, but you need to know both terms. Okay? So wherever there is a vertical asymptote. And the last type of discontinuity is something called an oscillating discontinuity. And you can see that that is not a focus in our class, so we're not going to talk about that. If you want to discover that on your own, go ahead and do that. But I do want to kind of summarize the three that we are going to focus on and how we can check them real fast. Removable discontinuity is when the limit as x approaches a number from the left is equal to the limit as x approaches a number from the right, okay? But it does not equal the function's value, right? So here's an example. Here's the curve, okay? At C here, the left-hand limit is approaching the same value as the right-hand limit, but they are not equal to the function's value. The function's value is missing. Now, if I put a dot here, it's not in the same place. It's removable. If I erase the dot, there's nothing there. It's still removable. Okay? For jump, the definition is the limit as x approaches C from the left is not the same as the limit as x approaches C from the right. So you have something that looks like this. Right? The left-hand limit is not the same as the right-hand limit. And it doesn't matter what the function's value is on this guy, because no matter what, you got to jump from one place to another. And then the infinite, if I could spell, discontinuity is when the limit as x approaches C from the left or right, not the best notation, of f of x is plus or minus infinity. So whenever you plug in a left or right-hand limit and get a positive or negative infinity out, you have an infinite discontinuity. and that's going to look like something like this, okay, where this is c, and again, we have a vertical asymptote there. So anyways, that is kind of a summary on all of those. Let's go ahead and take a look at how to determine these things analytically, okay? We've got, like I said, this lesson tends to be a little bit long, so feel free to pause it and then come back to it when you're refreshed somehow or another. But it tells us that h of x is equal to a piecewise x squared plus 2x minus 8 all over x plus 4, and that is for when x is not equal to negative 4. And then we have negative 3 when x is not equal to, or sorry, when x is equal to negative 4. Okay? So that's h of x, and the question is the function continuous over the entire, well, the interval from negative 5 to 0? Where is there any potential problems? Well, there's a potential problem at negative 4 because then we'd be dividing by 0. And that same problem of negative 4 is found in our break here. So let's go ahead and figure out what's going on. Now notice this part of the function, the upper part here, is everything except for a singular point. So what we're going to do is we're going to figure out by substituting what we get. So if I plug in negative 4, obviously, that's always a good idea to see if that matches. Essentially, I'm trying to figure out a limit here. So this is going to be 16 minus 8 over 0, and that's 0 over 0. It's indeterminate, okay? Now remember, when we're talking about discontinuities at a point, we're looking at limits. We're looking at the left-hand limit and the right-hand limit. So let's just go ahead and figure those things out. What is the limit as x approaches negative 4 from the left of h of x? Well, we just plugged in negative 4 and we got indeterminate out. So this is rational, so we're going to go ahead and factor it. So the top factors to, let's see, the limit as x approaches negative 4 from the left factors to x plus 4 times x minus 2 all over x plus 4. Why am I using this top function and not dealing with this? Because we're talking about the left-hand limit, so we're looking at values to the left of 4, not at negative 4. Sorry, left of negative 4. So we can see that these cross out, and we're left with that. So we have the limit as x approaches negative 4 from the left of x minus 2, which is going to be negative 4 minus 2, or negative 6. So the left-hand limit is negative 6. The right-hand limit actually is going to be the same thing because we're going to do the same work. Now, I talked about the idea of discontinuity here. Look, this canceled each other out, which means there's a removable discontinuity. The question is, did we fix that discontinuity by plugging in this point? And so if we were to graph this, we would have this x minus 2 come up like this, and at x equals negative 4, we have a removable discontinuity, and this should be negative 6 here, okay, because that's the limit that we got here. And the actual value at x equals negative 4 is negative 3, so that's somewhere up here, okay? So we can see that we have a removable discontinuity because the left-hand limit is negative 6, the right-hand limit would have been the same exact work, is negative 6. So let me go ahead and write that down. The limit as x approaches negative 4 from the left of h of x equals the limit as x approaches negative 4 from the right of h of x, but it does not equal h of negative 4, okay? Because this was negative 6, this was negative 6, but this guy was negative 3. And so we would conclude this function has a removable discontinuity at negative 4, and therefore the function is not continuous over that entire interval, okay? So since the limit exists but does not equal h of negative 4, the function is not continuous. It's a removable discontinuity at that point. Now, an extension question would be, what is the expanded equation that removes the discontinuity, essentially, that makes the function continuous? And so what we want to do here is basically take this point and move it down here. Okay, so we're getting rid of this guy and we're moving it down there. Well, what's the name of that function that would make it continuous at that point? Well, that's this guy. That's the reduced form. And so we would say, if we looked at this function, it would be the same function, but we fixed the problem, essentially. That's what it means to find the expanded equation that makes a function continuous. And so we'd just say y equals x minus 2. Okay. All right, let's look at another problem. This one is a little bit more direct in what it is asking for, because it's asking to determine what the limit is, or does the limit exist at a specific point. Okay, so we've got g of x is equal to x squared minus 9 over x minus 3 for x not equal to 3, and 1 for x equal to 3. And we're trying to figure out, number one, if g has a limit at x equals 3, and number two, if g is continuous at x equals 3. Remember, how do we know if there's a limit at a point? Well, the left-hand limit has to match the right-hand limit. So let's go ahead and figure that out. The limit as x approaches 3 from the left of g of x, and we've got to figure out the limit as x approaches 3 from the right of g of x. And then ultimately, we're also going to have to figure out g of 3. If we can figure out these three things, we can answer this question pretty easily. How do I figure out the left-hand limit? Well, let's just plug in that value into the appropriate place. Since we're talking about approaching 3, we're going to use the top function, not 3 itself. If I plug in 3 squared minus 9 is 0, 3 minus 3 is 0. We have indeterminate form. So we're going to go ahead and factor this. So that's going to be the limit as x approaches 3 from the left of x plus 3 times x minus 3 over x minus 3. We can see that those reduce, and so we're left with the limit as x approaches 3 from the left of x plus 3, which means when I go to substitute, I end up with 3 plus 3, which is 6. Okay. Now we'll do the right-hand limit. So we're going to do the same thing. If I plug in 3 again, we're going to use the same thing because we're looking at the places around 3, not at 3. And so we end up with the same exact work in this case. Sometimes it's not the same because the piecewise is defined maybe differently somewhere else. Okay. So we end up with the limit as x approaches 3 from the right of x plus 3, which is still 3 plus 3 equals 6. And some of you might say, well, do I have to write all that out? Yes, you do. I know it's repetitive, but it's showing step by step. And then what's g of 3? Well, g of 3 is 1. Now, what can we say? Does the limit exist at x equals 3? Yes, it does, because the left-hand limit and the right-hand limit are the same. So we'll say limit as x approaches 3 from the left, this is g of x, is equal to the limit as x approaches 3 from the right. Therefore, limit as x approaches 3 of g of x exists. Okay, so that's one answer. So 1 is true. And the next question is g continuous at x equals 3? Well, since the limit as x approaches 3, right, exists, it's 6, and, it's 6, and it's not the same as g of 3, which is 1, we would say, therefore, g is not continuous when x equals 3. And so that's our answer there. So 1 is true, 2 is not. And that wraps up that problem. Okay? So again, checking the limits, checking the continuity, and I actually like how it's written out here better than what's on the lesson. Went more in depth in terms of checking your left and right hand limits, even though it was repetitive work. Okay? All right, 2 more problems to go and we'll be done. This problem says, find any points where f is not continuous and then describe the types of discontinuities. This is an easy, quick problem. It really is. It's a cool problem. And it kind of checks whether you understand what we've been talking about. So if I have f of x equals x squared plus 3x minus 10 over x squared plus 9x plus 20, and we're looking for discontinuities, it's pretty easy to find out, okay? So what we're going to do is factor. So the top factors to x plus 5 and x minus 2. The bottom factors to, what is that? That's going to be 5 and 4. So x plus 5 and x plus 4. So there's our function just factored. This is exactly the same as this. It just looks different. We haven't canceled anything out, so this graph is the same as this. Now remember the quick trick that I showed you. A removable discontinuity is something that goes away if when you factor, things cancel out or the problem cancels out. So here's what I'm going to say. I'm going to say we have a problem, some sort of problem, when x equals negative 5 and x equals negative 4. Those are our two places that we have problems, because if I plug in negative 5, I get a 0 in the denominator. If I plug in a negative 4, I get a 0 in the denominator. Well, here's what we have. Since the x plus 5 and the x plus 5 can reduce, we would say that we have a removable discontinuity when x equals negative 5. We removed it, okay? This other one, it doesn't remove, it doesn't go away. So if I plug in negative 4, what do I get? I get negative 4 minus 2 is negative 6. Negative 4 plus 4 is 0. So I would get negative 6 over 0. Well, what do I get when I divide by 0? I get some sort of infinity. You see, what I did there was I took the limit as x approaches negative 4 of f of x. And what did I get? I got negative 6 over 0. Now, I don't really care, which is some sort of infinity. It could be positive, it could be negative. I don't care, because that's not what the question was. The question is just identify the types of discontinuities. An infinite discontinuity is one where the limit as x approaches a number goes to either positive or negative infinity. So it doesn't matter whether it's positive or negative, and it doesn't matter which side I'm coming from. So we would say we have an infinite discontinuity when x equals negative 4. So those are our two places where we have the function is not continuous, and those are the types of discontinuities we have. Again, if you can factor and cross them out, it's a removable discontinuity. If you factor and you can't cross it out, then it's an infinite discontinuity, okay? But if the numerator, like this one, where it says x minus 2, that's not a problem. You can have a 0 on the top. So if x is 2, you would get 0 overall. And there's nothing wrong with that. That's not a discontinuity. It's just an answer, right? So anyways, since the function can be reduced by x plus 5, x equals negative 5 is a removable discontinuity. Since x plus 4 cannot be reduced out of the function, it will be an infinite discontinuity. All right, last problem here. It says identify any vertical asymptotes of the function. Any vertical asymptotes of the function. Well, the function is f of x equals x plus 1 over x squared minus x minus 6. X squared minus x minus 6. All right, there's my function. I'm looking for vertical asymptotes. And listen, guys, I said this the other day. Students struggle with the definition of asymptotes. Remember, the horizontal asymptote is when the limit as x approaches plus or minus infinity of a function gives you some constant. So you would just take the limit as x approaches infinity and see if you get a number. A vertical asymptote is exactly the opposite. It's the limit as x approaches some number of a function gives you plus or minus infinity, okay? Because as we approach a certain constant, this is my constant, we're approaching infinity or negative infinity. So remember, what's another name for a vertical asymptote? It's a removable, sorry, it's an infinite discontinuity, okay? Well, how do I check for infinite discontinuities? I factor, so I got x plus 1 on top, and I got x minus 3, x plus 2 on the bottom. And so we can see that we have a problem when, when x equals negative 2 and 3. Does the problem go away? No, because nothing reduces. So these remain. Why is it a problem? Because we're dividing by 0. And remember, anything divided by 0 when you're taking limits is some sort of infinity, which means we have a vertical asymptote. So we would say vertical asymptote when x equals -2 and 3. Okay, and that is because if I take the limit as x approaches 3, I'm going to get a 0 here, and I'm going to get numbers here. So a number divided by 0 is infinity. Boom. If I plug in -2, take the limit as x approaches -2, I get a 0 there. These are going to be numbers. A number divided by 0 is infinity. So that is that. Vertical asymptotes at x equals -2 and x equals 3. Remember, vertical asymptotes and infinite discontinuity are the same thing. All right, so I gave you fair warning. This was a long lesson, but it's actually not as long as I thought it was going to be. But if you have any questions for me, if you need help on anything, please reach out. Probably the best way, honestly, is to comment in the YouTube video, because I get like notifications on that, I guess, and I can respond right there, and that actually helps everybody out if they see your comment or your question and then my response. Otherwise, it's going through Google Classroom and everything else. But again, if you need any help, reach out to me. Otherwise, I will talk to you later.